Exercise 6.9 is asking you to identify all of the electrophilic centers in each of the following compounds. Just for the sake of practice, let's identify all of the electrophiles and all the nucleophiles. This way we get more practice than the question is even asking for. But first, the electrophiles. Now you have two options here. You either have a full positive charge or you have a partial positive charge. So let's start with arachidonic acid. Arachidonic acid is a precursor used to make a lot of hormones, especially prostaglandins. And there are lots of different types of prostaglandins. But one thing the prostaglandins are famous for is they cause inflammation. So pain, heat, redness, swelling. That reaction to an injury is caused by this molecule, arachidonic acid, reacting and getting converted into something called a prostaglandin. So when this reacts and gets converted into the prostaglandins, so that you get that red heat, pain, and swelling, where is the molecule likely to react? Well, let's look for the electrophilic centers and the nucleophilic centers. First, the electrophiles. Do we have a full positive charge anywhere in the molecule? No. That'd be easy to see. It would be written in. Do we have a partial positive charge? We do. We have a couple. First, you get the positive partial charges when you have differences between electronegativity. The less electronegative atom loses its electrons to the more electronegative atom in the bond and becomes slightly positive. The carbon here is bonded to oxygens on both sides. Each of those oxygens steals electrons and becomes slightly negative, and that carbon loses its electrons, becomes slightly positive. Likewise, this hydrogen on the other side that's bonded to the oxygen loses its electrons to the oxygen and becomes slightly positive. So we have two electrophilic centers on this molecule. Now, again, just for the sake of practice, let's think about nucleophilic centers, and we're going to do it in the same way, one at a time. Do we have any full negative charges? We don't. Do we have any partial full negative charges would be easy to see because they would be drawn in. Do we have any partial negative charges? We do. We've already drawn those in on the oxygens. Do we have any lone pairs? We do. They're on the oxygens. Each oxygen has two lone pairs, another sign that those are nucleophiles. And then do we have any pi bonds? We do. We have a lot of them. All of these pi bonds can react as nucleophiles. And that's one of the reasons why arachidonic acid, which is an essential fatty acid, your body is the human body is unable to make it. The bodies of other creatures can make it even from just carbon dioxide and sugar. But humans can't make it. We have to get it in our diet. It's mostly in meats, although it is in a couple vegetarian sources of food. But the reason why it can make so many hormones, including so many different types of prostaglandins, each have their own reactivity and role in the human body, is because it has so many nucleophilic centers on this thing. So many places in this molecule can react and to form new molecules. So you can form a lot of hormones with this. Okay, let's use that same analysis to think about 2-heptanone, which is used to control the population of varroa mites in honeybee colonies. So a lot of these little molecules can function as hormones. Not just humans have hormones, but a lot of insects and plants will have hormones that can cause them to grow or be attracted to certain things. And one way you can sneak one sort of workaround, instead of using insecticides, you can use hormones that attract molecules and put those hormones away from where you want the insects to be. So for example, if this is a hormone that attracts these mites, you can daub it onto a wall near the honeybee colonies, but away from them, and all the mites will go to where you've put this molecule as opposed to the honeybee colony. You can do the similar thing with crops if you don't want to spray insecticides on them. So, to figure out where this molecule would be reacting with maybe receptor sites in the bodies of these mites so that they sense that it's there, you would want to try to look for the nucleophiles and the electrophiles in the molecule first. Do we have a full negative charge? We don't. Partial negative charge? We do. The oxygen is pretty electronegative. It pulls the electrons to itself, takes them away from the carbon, and so we see also that we have a slightly positive electrophilic center there. Do we have any lone pairs? We do. There are two on the oxygen. Another sign that that's a nucleophile. Do we have any pi bonds? We do. this pi bond here. Now, that pi bond is technically not as strong of a nucleophile as a pi bond between two carbons. Excuse me, because you'll remember that there is another resonance form of this molecule. When you have a pi bond between two atoms of different electronegativity, there's another form where there's a single bond there, and there's a full negative charge in the oxygen, full positive charge here. So that bond is really something in between a single and a double bond. So it doesn't have quite as much of a concentration of electrons as a carbon-to-carbon double bond, but it's still nucleophilic. And I should point out, we've seen this electrophile before. This electrophile is a really attractive electrophile. First of all, when carbon is double bonded to an oxygen, it's losing a lot of its electron density. For every bond it has to the oxygen, it loses more electron density. So already that's going to really attract nucleophiles in another molecule. Not only that, though, but when another nucleophile attacks, this carbon already has 4 bonds, and if a nucleophile attacks it, it's going to have to break one of those bonds. A pi bond is easier to break than a sigma bond. Remember, in a sigma bond, you get uninterrupted overlap between two orbitals, the standing waves of two orbitals, and that creates a strong bond. In a pi bond, you have parallel p orbitals that do overlap, but the overlap is interrupted. They overlap on the top and the bottom, but in between, it's interrupted because of the node in the p orbital. And so p orbitals are weaker pi bonds are weaker than sigma bonds, and so they're easier to break. So this is a really attractive electrophilic center, both because it has a pretty big slight positive charge, double bonded to an oxygen, and second, if a nucleophile attacks, the pi bond breaks really easily. So it's very accommodating to an incoming nucleophile. Okay, and so that's it for those. We can also check, is there a full positive charge, but there's not. And so we've identified all the nucleophilic and electrophilic centers in that molecule. If that reacts, it's going to react at one of those 2 positions. Or I guess 3 positions. All right, you eat hydrogenated animal fat. Let's say you have a Snickers bar. There's a molecule like this now wriggling first on your tongue, then in your intestines, then in your blood, finally in your cells. Your body wants to break this down and get energy from it. Where does your body attack this fat? This is a triglyceride. You can sort of see 3 tails, tri, and they're stacked on a molecule called glycerol, so triglyceride. Well, when the cells finally want to take this and get energy from it, they want to break it down, the places they're going to attack are going to be the places that are going to react will either be the nucleophilic centers or the electrophilic centers. So let's think about where those are. Do we have a full negative charge? No. That would be drawn in. It would be easy to see. Do we have a partial negative charge? Yeah, we've got quite a few. All these oxygens are electronegative, so they're going to pull electrons to themselves in their bonds and become slightly negative. Similarly, they're going to take those electrons away from the atoms they're bonded to. So those atoms are going to become slightly positive. Now, as we draw these in, notice how much richer the molecule looks with all these charges sprinkled over them, dusted over them. Next, do we have any lone pairs? We've got plenty of lone pairs because we have lots of these oxygens, and oxygen tends to have lone pairs on it. Each of these oxygens has 2 lone pairs, another sign that they could act as nucleophiles. Do we have any pi bonds? We do. They're not the best nucleophilic pi bonds because it's really a 1.5 bond because of the resonance, but sure, we have them. And then do we have any full positive charges? No. Those would be easy to see, they'd be drawn in. Notice that no reaction is going to happen in these long hydrocarbon tails. The reaction is all going to happen where you have those heteroatoms, the atoms different from carbon, or hydrogen, the oxygens. That's where you have the charges, and that's where your body's going to attack this molecule when it first tries to break it down. Just because that was a short exercise, and then 610 is another short exercise, I'm going to combine them into one video. This 610 is really asking you about the same thing. It says the following hypothetical compound cannot be prepared or isolated because it has a very reactive nucleophilic center and a very reactive electrophilic center, and the two sites would react with each other rapidly so that you wouldn't have this molecule anymore. Identify the nucleophilic center and the electrophilic center in this hypothetical compound. Well, let's go back to our table. Whenever you see a molecule and you're trying to think of how it will react, always identify first the nucleophiles and the electrophiles. So do we have any, and we'll think about these one at a time, do we have any full negative charge? No, that would be easy to see, it would be drawn in. Second, do we have any slightly negative charge? Sure, we have a couple metals here. Boron and lithium are both metals, so they have very low electronegativity. Whatever they're bonded to is going to be steal electrons from them and become slightly negative. Notice that lithium really has a lower electronegativity. Boron is more in the middle of it. It's in group 3A, whereas lithium is in group 1A. So lithium has lower electronegativity, and the slight negative charge on that is going to be bigger than on the boron, the atoms bonded to boron, because the boron has a higher electronegativity than the lithium does. So it can sort of attract the electrons back to itself better than the lithium can. Do we have any lone pairs? No. Do we have any pi bonds? No. So those are all our nucleophilic centers. Electrophilic centers, we have them. First, the lithium. It's losing its electrons to the carbon. And second, the boron. Boron is a metal. It's losing its electrons to the 3 carbons next to it. So we do have slightly positive areas. So what ends up happening here, if you try to have this molecule all by itself, is that the carbon nucleophile ends up attacking the boron, and it creates a ring. It creates a different molecule. Because you have a nucleophile, strong nucleophile, and an electrophile in the same molecule far enough on the ring, these bonds can wriggle around until these reach each other and a reaction happens, so that you would never have this straight chain. And so in other words, what that exercise is trying to illustrate is that just by being able to recognize nucleophiles and electrophiles, you'll have significant information about the stability of molecules and the ways that they can react.